Okay, so I want to quickly go through my own video on wave diffraction because I don't like the other teachers' diagrams. So there's quite a few other teachers' sites to look at, but mine are the best. I made my own video because I don't like these diagrams. So here we go. Remember, these are the list of things that waves can do, and they're the Sean words. So we've got reflection, refraction, total internal reflection, and diffraction. So they're all the TION words, and this is the last one we're looking at today. And all waves can do these. It's not just, we're going to talk about radio, we're going to talk about water, but all waves do this. So all waves can do all the things. You just need different media or different materials for them to travel through. So I could show you some pictures on the Google Earth of water waves and places where people build defenses, and defenses are often designed to have the waves come through and diffract, because diffraction's very reliable. Now, so let me just get rid of that. So diffraction is easy, and if we were at school, I could show you light diffracting with a laser, and we do a lot of that for the S5s, do diffraction with lasers, but ultimately we're going to mainly talk about water and radio today. Now, the key issue for all diffraction is the wavelength of the waves and the size of the obstacle or the size of the gap. So it's all about the wavelength and the size of the gap or obstacle. Okay, now an obstacle is really half of a gap. So I'll explain that as we go along. Just bear with me for a second. Here we go. Okay, so if the gap is the same size as the wavelength, we see lots of diffraction. So here I have waves. The waves are coming this way across the diagram. So the waves are traveling that way. And if I wanted to draw rays, they'd be going, these would be rays. These lines are actually representing the top of the crest of a wave. And so in physics, we call them wave front diagrams. But you don't really need to know that. Each one of these is crest of a wave, crest of a wave, crest of a wave. So in between we'd have troughs, we don't bother drawing them. And in this example, you'll notice that because the distance between the crests of a wave is a wavelength, okay, the wavelength stays the same across the diagram. And if you're doing this in an exam, it's an important one, is that this distance here, which is about 2 centimeters because I've measured it, it's about 2 centimeters there, it's about 2 centimeters all the way across the diagram. It's about the same. Even over here, this wavelength is the same as that wavelength. Now, because this wavelength is identical, I've chosen it to be identical in this case. So the wavelength is 2 centimeters, the gap is 2 centimeters, and we get loads of diffraction, which basically means the sound kind of goes around the corner and the sound waves fill in what you might expect to be a shadow zone behind the obstacle. So this is diffraction. It's waves bending out to fill in the zone behind an obstacle. And this happens really well when your wavelength and your gap size are very similar. So sound waves are roughly a meter in size. Middle C is probably about 80 odd centimeters or something like that. A doorway is a similar size to that. So if you make a sensible noise, it will go through a doorway and diffract, and people around the sides of a doorway will be able to hear the noise you make because of diffraction. Remember, diffraction is all about the wavelength and the size of the gap or obstacle. Now, while I've got a chance, I could just mention that if you've only got an obstacle, you could expect to picture something like this. If you don't have the other half of this wall that gives us a gap, then you don't really need it, because these waves don't know the other half of the diagram's there. They will just diffract around an obstacle that just pokes out as a lump. We'll come back to that later on. Okay, let's switch now. Now, if the gap is, so what's the next one? If the gap is a lot bigger than the wavelength, we see little or no diffraction. if the gap is a lot bigger than the wavelength. Now, this has challenged my drawing skills. So I've gone for waves that are about 1 centimeter apart, and then I've done a sort of 6 centimeter gap to try and show you. Now again, remember, these are crests. So that's a wavelength. This is a wavelength. And the wavelength stays the same all the way across the diagram. This is a wavelength. Now, because the gap is big and the wavelength is small, we don't get a lot of diffraction. So most of these, I could almost draw in sort of shadow regions here where we just don't get lots of diffraction. Okay, so it is very little diffraction, or no diffraction, because the gap is a lot bigger than the wavelength. Okay. Now, so if you look at light, light has a wavelength of 500 nanometers, so that's 5 in this column here. So that is unbelievably small compared to the size of a doorway, which means that if you shine a light through a doorway, you will not see light going around the sides and spreading out. It won't happen. You need to use a very small gap, similar to this wavelength, to spread light out. And you can spread light out if you have a small gap. Okay, and as I've just said, the sound, the G above middle C is almost exactly 1 meter in wavelength. And so voices go round corners. Okay, now, the old SQA questions that appeared a lot at National 5 were always about radio waves and television waves behind big hills. So let's focus on the key point here. A big hill like Ben Nevis might be 1,300 meters high. And maybe there's only a couple of hills that big in Scotland, but there's quite a few that are 1,200 meters high. Radio waves, long wave radio that you probably don't listen to anyway, is 1,000. Wavelength is big, 1.5 kilometers, 1,500 meters. So how does that work? Well, on my diagram, I'm going to start off with a wavelength, and I'm using this on this diagram. That's a lambda. It's not the best lambda. Okay, there's my lambda. 1,500 meters there. Now, if I put a hill in that's the same size, it will have to be about as tall as one wavelength. So here's my hill. I've slightly exaggerated it perhaps. And because I've drawn my hill as being the obstacle is about the same height as the wavelength, I get good diffraction. So if I drew a house, this house will receive these long wave radio waves, LW long wave, because they can diffract, okay? Because lambda equals the gap size, or in this case, the obstacle size. And remember, as I said earlier, that really an obstacle is half a gap, because this is a reworking of this diagram. Okay, if you can see, it's essentially the same diagram. So there we are. Right then, now on to TV signals. TV signals, and this is old style TV, like digital TV as it is now, they have wavelengths less than 1 meter. It's a bit the same with digital radio, if you've ever noticed. Okay, and so basically, I've tried to represent this by to try and get my diagram to scale. I've done them so close I can't mark in a wavelength. So I've had to do this magical illustration trick of sort of magnifying that to show you that in between these two lines I would draw a wavelength. But if my wavelengths are going to be 1 meter, and this is 1,340 odd meters high here, then obviously my diagram scale's a bit of a challenge. But the point is, if the wavelength is much smaller than the size of the obstacle, we'll get almost no diffraction. So here, the house will not get this TV signal. And using these conventional waves, and they'd have to do some, they're not going to get this TV signal because the TV waves are going that way. They are going that way, but they're not going to diffract because their wavelength is so much smaller. The wavelength is much less than the size of the obstacle, no diffraction. So those are my 4 diagrams for diffraction, which if you go back through the video, you should be able to freeze and look at the 4 diagrams and have a look back at the 4 diagrams and do your own sketches as part of your revision notes, or do your own sketches as part of question 2 in today's classwork task.